Hi everyone, so we are already done with the part 3b. Let's do the part 3c, which should be the last part in the shear links design. Right, now the next step is to determine whether the beam's VRD max is larger or smaller than the VED, through which we'll be able to determine the angle and hence the stirrups required. So here's my design shear force, the VED, which as we said, is to be measured from the shear force diagram at a distance of d from the face of the support. Although it is measured at a distance of d, shear links must extend to the face of the support up to the point where the shear force turns to its minimum value, and subsequently implementing just the minimum shear links till near to the next support, where it again turns to be maximum. Now let's define the theta. Remember when we said previously that the theta varies between 22 to 45 degrees. Yet how would I know whether my theta is 22 degrees or more? This is done by checking the concrete strut capacity, the VRD max. And in order to do so, the angle must be first assumed. So let's assume the angle to be 22 degrees. And this will only be true if the calculated VRD max was found to be more than or equal to the VED. Otherwise, the theta is not 22 degrees as assumed, and hence must be calculated using this equation. Alright, let the theta be 22 degrees and let the V, which is the strength reduction factor, to be as recommended by the Eurocode 2 as seen, and the FCD is 17 megapascal and the Z is 0.9D, which gives 405 millimeter. When all these variables are inserted, the VRD max is found to be greater than the VED. Simple as that. Which again tells me that the assumed 22 degrees angle is valid and there is no need to calculate the theta using this equation. I can now go ahead and find the area of reinforcement over spacing, so equating the VED with the VRDS. And by simple substituting the AS, W over S is found to be 0.386. Just to bear in mind that 500 megapascal is the yield strength of the stirrups and must be divided by its partial factor of safety. So in this case, always for the steel, it's 1.15. So what we have done here basically, we wanted to find the stirrups required. It is given by this ratio, and the VRDC, we equated this with the VED, and we have everything else that we need. Now, how would such a ratio help me place my stirrups? Well, by referring to this table below, it gives stirrup diameters against different spacing. 0.386 suits the best with the 0.402. And always remember to take a number a bit more than the one you found. So 0.402 means I'm providing 8 millimeter stirrups with spacing center to center of 250 millimeter. Alright, let's jump to this figure for a better visualizing. This is my beam under ultimate UDL with of course the corresponding shear force diagram. The distance X shows to what extent I must put the maximum shear links. That is 8 millimeter at 250 millimeter center to center. Alright, again, distance X should be defined along with the VRD minimum and its corresponding minimum shear reinforcement, which is this one here. So let's not get confused and first work out the minimum shear reinforcement. The rho W is given to be as following. It should be equated with the minimum, which is the rho W minimum, and this is given to be equal to 0.08 root FCK all over FYK. if this is worked out, it gives this small ratio. This is the minimum percentage of shear links. Then by equating the row minimum with the row W, and knowing that we are utilizing vertical shear stirrups, so the alpha here is going to be 90 degrees, plugging all the values there, this is what you get. The output is 0.26. This is the minimum ratio required. Now before going to that table, again, you might notice that 0.26 cannot be found in this table. Now there's one important parameter to be checked, that is the maximum spacing of the stirrups, which is said to be 0.5d times 1 plus cot alpha. Now the cot alpha is going to be a 0 since the stirrups I'm using are vertical stirrups, and the maximum spacing turns out to be 338 millimeter. Why would I do such a check? This is because unlike when designing the maximum shear length, spacing is going to be relatively less when compared with the shear lengths at the midspan, where the minimum amount is kept, resulting of course in larger spaces. Again, 338 millimeter is the maximum allowed. I'm going to be more conservative and I'm going to take it as 300. So the 300 here, and well, from this table again, 0.335 is the closest. So I'm selecting 8 millimeter at 300 millimeter center to center to be my beams stirrups at the mid span. Let's look at this diagram again. I have just conveniently selected the stirrups required to take care of the shear forces at different locations, from the maximum near to the support to the minimum at the midspan. Yet I don't know to what distance I should extend the stirrups of both values. This would be done if the VRD minimum is determined first. So let's work it out. Again, if I have my stirrups for the minimum required, well, then I can manipulate with it. If the minimum ratio is 0.335, then this is also logically corresponding to the minimum shear force, this one here. And so by rearranging the equation, the VRD minimum can be worked out to be 147 kilonewton. So that's it. I have all what I need to find the X and, well, the X at the midspan as well. So let's do it. From the diagram, the VEF and the VRD minimum are both useful now. Okay, both of them. Since the maximum stirrups extend from the face of the support to the point it turns minimum, X is equal to the difference of the two forces by the ultimate load. Alright, when solved, it gives a distance of 765 millimeter. Okay, so the X is 765 millimeter. Let me call the space at the mid the X mid, and half of this distance is again going to be the VRD minimum over the ultimate load. You can also apply the similar triangles in order to solve such kind of distances. Now for each X, how many shear lengths I can fit into these spaces? For the first one, for the first X, it is simply equal to 1 plus X over S, alright, for this region. This is going to be 4.06. Now here is this one here, the one, number 1. This is because I'm measuring the distance center to center. So it turns out to be 4.06. Well, I must take it as a whole number. 4 is the correct answer, but I can also take it to be 5, and that is also correct. So let me take it as 5. This will lead to a change in the distance X. So what was 765 millimeter is now 1 meter. So X becomes 1 meter, 1000 millimeter, and this would also mean a reduction in the X mid. So half of it becomes 1850 millimeter instead of being 2.085 meters. I can also tell how many stirrups to fit in the mid span. That is simply 7, just the same procedure as what we did previously. So this is going to be a total of 14 stirrups at the mid span. So that makes it the shear links design. That's my section with the bending rebars and the shear links as well. So we have covered almost all the design aspects. What remains is the detailing, which hopefully will be covered in the next parts. Thank you very much for watching.